So we haven't looked at any aspect of time so far in anything we've done. So for example, when we looked at the rotating phasor in the graphical calculator, the speed that rotated was really arbitrary. It was just determined by whoever produced that program. So for example, they could have set it up so it took 1,000,000 years for the phasor to rotate round, which would be rather silly, or they could have went to the other extremes and they could have allowed the phasor to rotate at an extremely high speed, so it would only take nanoseconds for it to rotate and you wouldn't see anything. So in that case there, the rotation is quite arbitrary, but we don't want that. We want to be able to control or have some defined means of controlling that rotation or defining that rotation. Now what we've got drawn out here is a simple y-x axis, and we had our angle theta and we had a length of our phasor A. Now from simple trigonometry we can say that y upon A is equal to the sine of the angle theta. Now I've actually put y as a function of theta because that's what's happening here. We're interested in how y changes as the angle theta changes. So we could say y as a function of theta is equal to a sine theta. So there shouldn't be anything new in that. But as theta turns round, we're interested in the time it takes for it to go round. So we're interested in the function theta as a function of time, and we don't know what that function is. Now what we do is we define something called the frequency. Now the frequency is defined as 1 Hertz, which would be 1 revolution per second. So if it takes 1 second for that to turn round, 1 full revolution, then it is travelling at 1 Hertz. So let's extend on that a little bit. We could say that 1 Hertz is equal to 2 pi radians per second. So rather than having it in degrees and saying it's 360 degrees in a second, we tend not to deal in degrees, we tend to deal in radians. Okay, so that's equivalent to 2 pi radians per second. Now let's say for example it wasn't travelling at 1 Hertz, let's say it was travelling at 5 Hertz. Then it would be going 5 times as fast. So it would travel 5 times 2, which would be 10 pi radians in a second. So therefore you could say it's travelling at 2 pi f radians per second. Now if we waited for 5 seconds, then the total angular distance that it would have covered would be the 2 pi times 5, which would be the 10 pi radians, times the 5 seconds, which would be 50 pi radians. So it would have travelled in total 2 times pi times f times t radians. So 2 pi ft radians. So let's finish this off now. We were interested in theta as a function of t, so we've realised that theta as a function of t can be written as 2 pi ft, so that would be the total angular distance travelled in radians as a function of time. But we tend not to write it out like that, we tend to shorten it, and we introduced an idea of something called the angular frequency, which is radians per second. So the angular frequency is given by 2 pi f, and that's in radians per second. So it means that we can say that the y is a function of theta, so we know that y equals a sine theta, but we know that theta is also our function of time, which is equal to our omega t. Now we can also add in an extra term here, which would be the phase, so that would be determine whereabouts within that circle the phasor started to rotate, so we could add that on as an extra term phi. So if we were to bring both these together, we would end up with an equation which would be y of t is equal to a sine omega t plus phi. So that really gives us the height y at a time t, and it's dependent on the initial starting phase, it's dependent on the frequency and the time, and also the initial amplitude as well. So now if we were to take what we've just learned there and we replace the angle theta with the angle omega t, then we could say from our equations we had before, e to the I theta equals cos theta plus I sin theta, and we could replace that with e to the I omega t equals cos omega t plus I sin omega t. Equivalently, we could write e to the minus I omega t equals cos omega t minus I sin omega t. Now, this is our complex exponential, e to the I omega t. Now, we're assuming that this case here, there's a 1 there in front of it, so it could be any number. It could be a e to the I omega t, and that would just change the amplitude. So let's have a wee look and see what that looks like, and we'll also have a look at it in MATLAB. So I've got it drawn opposite here. We've got the real axis here. We have the imaginary axis. Now, remember, this is different from what we've seen previously in the last slide. Last slide we were looking at the real axis in x and the real axis in y, but now we've got the real axis in x, but it's an imaginary axis in y, so this is a complex plane here. So what we're going to do is we draw out the complex plane, but then we'll also add in time here as well. So now the time becomes that extra variable. So if we were to draw this complex exponential out, it would look like a corkscrew rotating as time increased, just like that. Now, that's split into two parts. There's an imaginary part and a real part. So the imaginary part of that e to the I omega t is the sin omega t part, and the real part of the e to the I omega t is the cos omega t part. So if we were to look in from this angle here, what we would see would be the sinusoidal function. And if we were to look from above down onto this corkscrew, what we would see would be the cosine function. This would be the imaginary part of e to the I omega t, which is our sin omega t. This would be the real part of e to the I omega t, which would be our cos omega t. And the summation of this would be cos omega t plus I sin omega t, which would be this corkscrew. Now I'm going to be drawing out a few of these three-dimensional drawings through the rest of the course. So let's have a look at this in MATLAB. So that's what we're looking at here. So again, we've got the imaginary axis here, okay, and we've got the real axis. So the real axis in effect runs up here, okay, and that's the time axis there. Okay, so there we have our corkscrew there, and there we have, if we look in for that angle there, we have our sine, okay, and then from that angle there we have our, looking at the real axis is our cosine. So let me see if I can just get this into the same kind of format. So you see this here. Now what I'll do is I'll actually turn it, and if I go to this plane here, which would be the imaginary plane, so we're expecting to see, in the imaginary plane, expecting to see the sine, okay? So if I switch this round, I'll actually go all the way around like that. Let's see, so there we come in. So that's us coming in here, yep, okay. And trying to get it, there we go. Okay, so that's exactly what we're seeing. We're looking in, we're seeing our sine wave, okay. Now I can just bring it back round, okay, so there we go. Again, that's us looking there. So that was our looking at our sine. Now if we were to go in and look directly from above, okay, well we would expect to see our cosine. So we come in here and we look at it, try to get it so you can see it changing directly from above. So that's, we're coming round and we'll spin it right round. That's us looking directly from above, and we will get our cosine, okay. It just runs down that way because I would have to turn it round 180 degrees, wouldn't I, in order to get it for like that. So there we go. That's us looking in right from above, and that's us getting our cosine there, okay. So that gives a good indication. Obviously you can look in directly from this end here all the way through, and all you'll see is just your circle, okay. So we come in here and all you've got is your real axis and your imaginary axis, okay. So that gives a good indication. I suppose a picture paints 1,000 words. Okay, so that's your complex exponential done in 3D, and you can see the cosine part and the sine part. So let's finish off this introduction of time into everything that we've been doing, and we'll see how it affects how we write the Fourier series. Now we've seen the Fourier series here, I've rewritten it here just as a reminder, and we've worked through that and we've derived it. But there's a problem with this. It can only approximate functions of period 2 pi because the sine and the cosine are functions of period 2 pi, so they will end up with the crossover point being multiples of that 2 pi. Now that's not much good. We want to be able to approximate any function. So for example, we might have that square function there that has got a period of 10 pi, but the sine function, the cosine functions, have got period 2 pi, so they'll have a zero crossing at that point. We don't want a zero crossing there. The zero crossing can occur here and only here and here. So what we have to do is we have to scale the axis. But what we can do, in order to get that from 2 pi, from 10 pi to 2 pi, well, it'd be equivalent to saying 2 pi upon 10 times the 10. Those cancel out and you're left with the 2 pi. So in effect you're multiplying by a factor of 2 pi upon the period here, which is 10 pi. So we call the period L, then that's equivalent to multiplying the whole thing by 2 pi upon L. So we know that we're using factors of n as well, so what we're going to end up with is n times 2 pi upon L x. So this 2 pi upon L is a scaling factor which allows us to approximate functions of varying periods. So let's finish off and we'll add the idea of time into our Fourier series. So we'll represent a function of time and a function that has got any particular period. So we know that we could write the complex exponential as e to the I omega t, but in terms of the Fourier series, we're using integer multiples of a fundamental frequency omega naught, so we'll call the omega omega naught, and we've got the integer multiples which are n, so you end up with e to the I n omega naught t. So that's going to be our cos n omega naught t plus our I sin n omega naught t. But we can expand this out. We can write it as cos n 2 pi ft, and we can write it as I sin 2 pi ft. And we know that frequency is 1 upon the period. The period is t naught. So that can be written as cos n 2 pi upon t naught t plus I sin n 2 pi upon t naught t. And again, all we're looking at here is the 2 pi upon t naught and the 2 pi upon t naught are the scaling factors which allow us to represent a function of any period. In the same way we see in the last slide, we had 2 pi upon L. L was the period. So let's put this into our Fourier series. So our Fourier series with respect to time is going to be f of t equals a0 plus the sum from an of cos n omega naught t plus bn sin n omega naught t. And we can find our coefficients a0, the ans and bns. The a0 is going to be 1 upon t naught, the integral from 0 to t naught. The an will be 2 upon t naught, the integral from 0 to t naught. And the bn will be 2 upon t naught, the integral from 0 to t naught. And you can see how you got the 1 upon t naught. Previously, to find that value of a naught, it was 1 upon 2 pi times the integral from minus pi to pi. But now, the value of 2 pi is simply the period. The period is just t naught. And again here we can go from minus pi to pi, which is a total of 2 pi. So that's equivalent to going from 0 to t naught, which is just the period of 2 pi. Well, in this case, whatever the period is happens to be t naught. Now, the same thing happens with our ans and bns, but this case here, we found our ans and it was 1 upon t naught, so it was going to be half of the period. Okay, so it's going to be a half of the 2 pi, so it's 1 upon a half. Okay, so it must be double it, so in effect you end up with the 2 upon t naught. And the exact same happens for the bn as well. And the full period again is going from minus pi to pi, so it's over 2 pi, so it goes from 0 to t naught. So that's how these change, and that's how we get this form here of the Fourier series, which you're probably used to seeing if you're doing any electrical engineering. So we'll go ahead and we'll do an example of the Fourier series using this form here. So thank you for listening, and goodbye.